Okay, welcome Year 11 to Physics paper 2, separate content only. This is going to cover just the separate content that comes up in the paper 2. There are 4 topics in this: forces, waves, magnetism and electromagnetism in space. And we'll try and just whistle through some of those separate only content pieces that we're expecting to be examined in the exam. So let's have a quick look and see what we've got in forces. Okay, in forces, we've got drawing force diagrams, moments, levers, gears, fluid pressure, so pressure at different depths in water, upthrust, force upwards due to being in water, and atmospheric pressure, so the pressure of the air above us, and applying the rate of change of momentum equation. So let's get started. So with force diagrams using vectors are a way of showing a force being applied to an object, and quite often you might get 2 forces being applied to an object, and you might be asked to work out the resultant force. So we've got this smiley face being pulled by 2 forces, the length of the arrow telling us the size of the force, and the direction of the arrow telling us the direction of the force. Now to work out a resultant force of 2 or more forces, you're going to draw them end to end. So you've got to move one of them effectively, and the resultant force will be from the start of the first arrow to the end of the last arrow. And you can so to do this, you're going to need a protractor. You're going to measure the length, a protractor and a ruler. You're going to measure the length of the one you want to move, and the angle from the horizontal. So this little angle here, measure the length of it, and then you're going to move it to the end of one of the other forces. So your resultant force will now be from the start to the end of the second force, and so this now is your resultant force. Okay, now if you've got three or more forces acting on an object, to find out if the forces are balanced and the resultant force is 0, we simply add the forces end to end again, and if they form a closed loop, as in they end up at the start again, the resultant force is 0. So let's have a look at this one. You'd measure the length of it, you'd measure the angle of it, and you'd place that up at the ends to end. And then with our last one again, you'd measure the length of it, measure the angle from the horizontal, place it up at the end there. And so this one forms a closed loop. So it means that there is a 0 resultant force acting on the object, meaning it would stay at a constant speed or stay stationary. Okay, moments and levers then. So a moment is like a turning force. So let's say we've got a spanner with a nut there. It's going to pivot, it's going to turn around the centre of the nut there. So your spanner would turn around that way, and we have a moment due to the force that's being applied, so 100 newtons in this case, times the perpendicular distance. Now perpendicular distance from the pivot means it's basically a straight line, 90 degrees to the direction of the force that's being applied. So the force is being applied downwards. The perpendicular distance is this distance here, and of course that wants to be in meters, so you'd convert your 15 centimeters into 0.15 meters. Okay, in different situations, the pivot might appear in a different place. So on a hammer, you'll be applying, if you want to use a hammer to lift up a nail here, the effort would be applied at the end of the hammer. So your perpendicular distance would be 90 degrees to the force being applied. So that would be your perpendicular distance there down to the pivot, and our load is on the other end of the hammer there. And the same with scissors. So scissors, they would pivot around this place here. You've got a load force and an effort being applied there, and you could use our equation again of moment that you're applying to the scissors there is equal to the force applied times again by the perpendicular distance, which would be from the effort to the fulcrum to the pivot. Okay, now for an object this applies to seesaws, this idea of moments. So if we look at a seesaw with Garfield and Fido, is that his name? Fido on it? For an object to balance, then the clockwise moment must equal the anti-clockwise moment, as in the force of Garfield times by the distance of Garfield from the pivot must be equal to the distance of Fido times by the weight of, oh, it's not Fido at all, is it? It's Odie, while I live and learn. So now, if you've got multiple things on one side, if you've got another object over on this side of the seesaw, the moment of this object plus the moment of this object would add up to the moment of OD. So you would simply just add their moments together, and if it's in balance, they should add up, and they should be equal to each other. Okay, so gears. There's not a huge amount of detail around gears, but worth knowing the little bit that is in there. So gears, like in a car or on a bicycle, are discs with teeth around the edge. They transmit turning forces from one place to another. They can be used to increase the moment of a force or reduce the moment of a force. And when we look in a bit more detail, well, if we've got a driving gear, so that's the one where you're applying a force to, and you've got the driven gear, the one that you're getting the force to be transmitted to, increasing the size of the gear increases the moment. And that's because there is a larger distance between the pivot and where the load is where the effort is being placed over here. So the bigger the wheel, that's increasing the moment. And the opposite way around as well, if you're driving a big wheel here and that's attached to a smaller one, well, then you're going to be reducing the moment as the distance between the force being applied and the pivot there is smaller. Okay, so fluid pressure. Pressure increases with depth. So if you had a can with holes in it at different depths, you'd see that the pressure would be highest at the bottom, and hence the water would be coming out further. So as depth increases, so does the number of particles above that point. So as you go down, there are more particles above that point. The weight of these particles adds to the total pressure. Okay, now there's an equation for pressure at depth. So now pressure equals rho G times H. Rho being the density of the liquid, G being the strength of gravity, and H being the height of the container. So fluid pressure, so the pressure inside a liquid, it doesn't depend on the shape, doesn't depend on the total mass of the liquid, and doesn't depend on the surface area of the liquid. So you can see in these three different shaped objects, the pressure at this depth just here would be exactly the same in all of them. Okay, so pressure equals rho GH. Okay, now atmospheric pressure. So if we look at a little man up a mountain, or a little man at the bottom of a mountain, at higher altitudes, air pressure is less. And this diagram helps us to see why that is. So the higher the altitude, the higher up you are, if you're up here, the higher the altitude, the less air there is above you, the fewer air particles there are above, so they press down with a smaller force. And the further down you are, the more particles there are above, so they're pressing down more, meaning that all the particles are closer together because there's a bigger force pushing on all of them. And if we were to draw a graph of air pressure against altitude, against height above the ground, we would see that the pressure is very low when we're really high up in the atmosphere, and you can see it steadily increases as you get closer towards the ground. Okay, so upthrust. So this is to do with things floating. So why do things float then? If we have a look here at an apple floating in some water, well, the apple is displacing some water. So the apple is pushing this amount of water out of the way. The size of the upthrust force is the same as the force of the weight of the water that has been displaced. So you'll have pushed some water out of the way with the apple, and the weight of that water being pushed out of the way is the same as the size of the upthrust force. So that's why ships need a large volume below the water so that they can carry lots of heavy goods, because the bigger the volume of water they push out of the way, the more mass and more weight of the boat they can carry. Okay, so how can we explain this upthrust force? So why does a cube of ice float upwards when in water? So if we take our cube of ice and we have it deep underneath the water, well, what do these arrows tell us? What are these arrows from? So pressure increases with depth, as we saw earlier. So the further down the ice cube is, the more the pressure is. But even on the edges of the ice cube, at the top of the ice cube, there will be less pressure than there is at the bottom. So the base of the object down here will feel a higher water pressure than the top, meaning that overall there'll be a resultant force upwards, and this is called upthrust. So down the bottom, there's more force, there's more pressure acting on it than there is from the top. So overall, we're going to have an unbalanced force upwards. And the upthrust is equal again to the weight of the water displaced. Okay, so applying the rate of change of momentum equation. Crumple zones in a car, airbags in a car, seatbelts in a car, gym crash mats, cycle helmets, playground surfaces. All of these things keep people safe in an accident, and they all work in the same way. So all of these safety features, they reduce the forces on a person. And it's those forces that will hurt someone, that will injure someone. And how do they do that? Well, they reduce the rate of change of momentum. So if we need a reminder of what momentum is a measure of your mass times your velocity. So when you're in an accident, when you're stopping, you hit a crash mat or you hit an airbag in a car, you go from a high speed to a low speed. And that can't be changed. Inevitably you're going to have to go from that high speed to the low speed. And that is the same as saying you're going to go from a high momentum to a low momentum. Now we can't change that change in momentum. You're going to have to go from high to low no matter what. But if we can change the rate of change of that momentum, as in we can make that rate of change happen over a longer period of time, it's going to keep you safer. So all of these safety devices, they all make going from a high momentum, as in fast, to a low momentum, as in moving slowly, they make that occur over a longer period of time. In other words, they make you stop slowly instead of stopping suddenly. It makes a lot more sense when it's said like that. So how can we prove then that to reduce the forces on a person in a crash, we need to increase the time they stop over? How do we know that? Well, F equals ma tells us that in order to reduce the forces, if I want to reduce that number there, I have to reduce the acceleration. And that's because in an accident, we can't suddenly become lighter, so I can't change the mass of a person in an accident. I can only change their deceleration. So how do I reduce their deceleration in an accident then? Well, if we have a look at a equals v minus u over t, this tells us that to reduce the acceleration, well, we can't change the final speed and start speed. That's going to be from very fast to stopped. We can't change the speed change in an accident, but we can change the length of time that speed change occurs over. So to reduce the deceleration, we have to increase the time taken to stop. Now that leads us on to our equation, the rate of change of momentum equation. So when we combine F equals ma and we swap a for v minus u over t, when we combine those two things, we're left with F equals mass times the change in speed divided by the time that occurs over. And that is the rate of change of momentum equation. I would recommend in a question, just as I've shown you before, underline the numbers in the equation, and then so if you've got maybe 15 kg and 2.0 seconds, just underline those things and write above them what they are. This is an equation you get given, so on the equation sheet you can pick it out, but if you've already written down those symbols for it, that'll make it a lot easier for you to pick out. Okay, so on to the waves topic. So refraction and reflection, uses of electromagnetic waves, lenses, images, ray diagrams, black body radiation, sound, ultrasound, visible light, and how we see colour. So when light hits a surface, it can be reflected, transmitted, or absorbed in different amounts. So here we have some sunlight hitting a window here. We can see that some of it is absorbed into warming the glass of the window. Some of it is transmitted through, and some of the energy is also reflected as well. Now, reflection happens in 3 different ways. So if light hits a surface, for example, if it hits a wall, we would say it has diffuse reflection. We can see light being reflected from the wall, but we can't see a picture coming from the wall. And that's because diffuse reflection is where the light is scattered and scatters in all different directions. So we don't end up with a picture, but we can still see the wall because light is being reflected from it. Now, specular reflection is for smooth surfaces. So specular reflection is where the light hits and leaves at the same angle. And this would be, for example, a mirror where you can see an image clearly in the mirror, or maybe reflected from a window if you're at the right angle. Now, the law of reflection states that the angle of incidence equals the angle of reflection. So this angle of incidence, to start off with, we have to draw our imaginary line, our normal, and we draw that at 90 degrees to the to the wall, to the surface. Our angle of incidence is between the incident ray, the ray coming in, and the normal, and our angle of reflection is between the normal and the ray. Okay, so really important to remember to draw that normal, and that our angles are measured from that normal. Okay, so far so good. Okay, so refraction and reflection. So this should be an image burned into your memory of a ray of light going into a block. And again, we're going to draw that normal 90 degrees to the surface, and it can even go into the block. And our angle of incidence is going to be again drawn between the incident ray and the normal. Our angle of refraction drawn between the refracted ray and the normal. And we're going to see that as it goes into a more dense material, it slows down, and the wave slows down and it bends towards the normal because it's entered a more dense medium. And on the way out, the wave is going to speed up and bend away from the normal due to entering a less dense medium. Now, if we shine the ray of light straight down the normal, the wave still slows down, but it's not bent because it's entering the wave along the normal. And we get to see now in this diagram why exactly that happens. So a beam of light could be drawn as having little peaks and troughs. And these lines here could represent a peak of the wave going into the block. And we can see the wavelength there is the distance between the two lines. So as the wave hits the denser material, it slows down. Now when we look at this wavefront here, the right-hand side of the wavefront, as we're heading into the block, the right-hand side of the wavefront hits the block first. That part slows down first. As that slows down, the rest of the line is still moving quite quickly. So it has the effect of making it turn into the block there. So you can see the angle has changed. The wave has slowed down, and because the wave has slowed down, the wavelengths have got shorter, but the frequency has stayed the same. Okay, and here we can see those same wavefronts going into a block at 90 degrees. When they're at 90 degrees to the surface of the block, again, they'll slow down, so they won't change direction. The wavelength will just get shorter. Okay, so uses of electromagnetic waves. So here are a few uses of them, and for separate science you need to know why they're useful, why they're suitable. So long wave radio is good for long distance communications, and the reason why is because it can bend or diffract around the surface of the Earth. So it doesn't travel into space. Basically, it'll bend around the surface of the Earth. Medium wave radio is a slightly higher quality radio communications, and this one can reflect off the ionosphere. So again, it can travel pretty long distances. The more it reflects, the more the signal will be deteriorated, and the worse the signal will be. Shortwave radio is a high quality communication, so Radio 1 will broadcast on that, for example, and that'll travel slightly less far, but again can reflect off the ionosphere or the atmosphere. TV signals and radio are used for high quality communications. Again, this is a very short wavelength and only works in direct line of sight, so you have to be able to see the tower broadcasting the signal, and won't work too well in valleys. Microwaves for satellites, so we can use Earth to satellite communications, and this is because it can pass through the atmosphere. It doesn't diffract, it doesn't reflect, and it's not absorbed by the water in the clouds there to reach the satellites. Microwaves for cooking, so this is for heating, and the wavelengths can be absorbed by the water molecules. So those water molecules will start to vibrate, and as they vibrate, they'll bump into other molecules and then warm them up. Using infrared, so that's used for night vision. All objects give out infrared. The hotter, the more it gives out. And we can use infrared for cooking as well, so toasters and grills might use that. Infrared causes objects to heat up, like grilling your toast. Okay, infrared heaters, so again, using them for heaters is a bit like using them for a grill. It causes objects to heat up, like the room. Visible light, so we can use that in fibre optic broadband communication. How does that work then? Well, light will reflect off of the walls of the glass fibre. You'll have a tube of glass there, and light will just internally reflect off of the inside walls there until it reaches the end of the fibre. Ultraviolet is used in sunbeds, so it simply causes tanning of the skin. Ultraviolet can be used in security ink. So for example, in paper money, they use it there. So ultraviolet light will hit the fluorescent ink. It gets absorbed, the UV gets absorbed, but then it emits visible light. Because don't forget, our eyes can't see UV, but they can see visible light. So that's why the note will appear to glow, because it's turning that UV into visible light. UV in energy efficient lamps, so ultraviolet will hit the fluorescent material on the inside. This is where we've got a long strip light, maybe in your kitchen or in the classrooms that you're taught in. So it hits the fluorescent material on the inside of the tube there, and that will be absorbed and emitted as light again, similar to the security ink. X-rays in imaging then, so for using for X-rays, they pass through flesh, but not bone. So they're absorbed by bone, and they pass through flesh. Now they turn a white detector plate, they turn it black when they hit it. So you'll be familiar with the X-ray with maybe a skeleton of a hand on it. That's obviously a skeleton I'm drawing there. But the outside is black, isn't it? And the bones are white. That's because the bones are absorbing the light. The black is where the plate is turned black because it's absorbing the X-rays are hitting the plate. Okay, gamma rays and X-rays, well, they're used for cancer treatment. That's simply because they kill all cells, and they'll be shone at the cancerous cells. But then the source will be moved around the patient so that so that the healthy cells don't receive too much of a dose. That they're kind of trying to spread the harm done across the healthy cells. So gamma rays can be used as medical tracers. So that's where a gamma emitting isotope can be traced as it travels through the body. So someone may drink a medical, a radioactive meal, a tracer. They may drink it or breathe it in or be injected with it, and it'll go inside their body, and the radiation will pass out through their flesh and will be received on a detector, so that doctors can have a close look at the function of kidneys or stomach or lungs or heart, whatever it may be. Okay, so now we're on to lenses, images, ray diagrams. So this type of lens then is a convex lens, and convex lenses, well, they focus the rays of light down into a focus past them, and the point where the rays will cross over is called the focal point or the focus, and this distance here from the center of the lens to the focus is called the focal length. And the other type of lens is called concave. You can see my using my imaginative teaching methods there. Cave because it is like a cave. Genius. And they will make the rays of light spread out as they go through the lens. Now, because they spread out, you might think, well, where's the focus point then? So this is where we have to draw those imaginary lines backwards. Drawing those imaginary lines backwards shows us where the focal point is behind the lens. Now, magnification equals image height divided by object height. So apologies if these don't quite fit on the page here. So magnification equals the image height divided by the object height. So let's just have a quick think about that. If I'm looking at an object, for example, a tree, and I'm looking at it on my phone, on my mobile phone, it's going to be the image of the tree is obviously going to be smaller than the object. My magnification is going to be between 0 and 1 because I'm shrinking the object down into an image, so my magnification is between 0 and 1. If it's the other way around and I'm looking at maybe a cell, a tiny microscopic cell with a microscope, and I need to see that image bigger on a screen for me to be able to see it, well then my magnification will be bigger than 1. Because my image will be a bigger number than the object, and a bigger number divided by a smaller number will always give you a number bigger than 1. Lovely. Okay, so some of the rules then about how we draw ray diagrams. So the rules are, if you've got an object here, an arrow, an upwards facing arrow, could be any object, and here's my lens, and sometimes the lens may only draw the lens as being small. You can assume that the lens covers that entire strip there, and so where the rays hit it, even if the rays hit down here, you can still think of that lens as acting here, so they'll be bent by the lens. Okay, so what are the 3 rules then? Okay, so you're going to draw a ray undeflected straight through the lens, like so. So from the top of the object straight through the center of the lens. You're going to draw a ray parallel to the axis, and then it's going to go parallel to the axis, and then it's going to bend through the focus on the other side. So you're going to need to draw it a little bit more carefully than I have here. Should go exactly through that focus. And then if you need to, you can draw a third ray, which this time goes through the focus on the left-hand side of the lens. And so there will be a focal point on you can draw one on both sides there. And that will then hit the lens and go parallel to the axis. Now the image is going to be formed where those rays cross. Okay, if the rays don't cross, there's no image formed, or maybe you've drawn them wrong. So now what can we tell about this this image here then? So this image is inverted. Inverted just meaning upside down. It is diminished, or we can say it is smaller than the original. And now this one is a real image. The reason why this is a real image is because it's on the opposite side to the lens. We could put this on a screen. So I could have a screen here, and this would be me projecting my object onto the screen. We'd be able to see it, it'd be in focus, and it'd be nice and clear. So we call it a real image. Okay, there's another example now. This would work for, this is still a convex lens, but this technique could work for concave lenses as well, where the rays spread out. If we have a look here, we've placed the object inside the focal length. Now, placing an object on the focal length will mean that your image is exactly the same size as the object. But if we place the object inside the focal length, it's actually going to make something a bit weird happen to the object. So let's have a quick look then. Let's apply our 3 rules. So there's our 3 rules again. So draw a ray undeflected straight through the lens. Hey presto. Draw a ray parallel to the axis, and then when it hits the lens, go through the focal point on that side. Now, we can notice here that the rays are spreading out. So they're never going to form a real image on the right-hand side of the lens. So where will they form an image? Where would we see the image appear? So we can draw a third ray if we need to, or we could just use these 2 here. Okay, the third rule is still going to draw a ray through the focus on this side, and it's going to come up to the lens and bend parallel to the axis again. Now, when we cross those rays over, when we draw them backwards with imaginary lines back off into the distance, we see that they cross over in the same spot, which is lovely because that tells us where our image is. So our image, and we're going to be able to say a few things about our image. Okay, our image, because it's behind the lens, it's going to be virtual. We're going to see the image as if it was behind the object. It is upright, so it's the same way round as the object, and it is magnified because it's bigger. Okay, black body radiation then. So black body radiation is to do with the colour of objects, and as you hopefully know, that black objects, dull black objects, are the best absorbers of heat radiation. They're also the best emitters of heat radiation. Shiny silver being the worst absorber and worst emitter, but best reflector. So, the colour black is not only the best absorber of heat radiation, but also of all electromagnetic radiation, whether it be gamma rays to radio waves. A black body would absorb all of the electromagnetic radiation that hits it. They would also be the perfect emitters of radiation as well. So a black body, it won't reflect or transmit anything. So you won't see any reflections, it won't let any energy pass through it. It absorbs all of the energy that hits it, and if it's at a higher temperature than the surroundings, it will be a perfect emitter of heat radiation. It would emit all of the radiation possible. Now, a perfect black body doesn't really exist, but it helps us to understand some physics ideas. So while this is a theoretical object, it can help us to understand things which are close to being perfect black bodies. Okay, so let's have a look at them. As objects get hotter, the intensity of the peak increases. What does that mean, the intensity of the peak increases? Well, when objects are hotter, it basically means they give out more radiation. If you could see that radiation, it would appear brighter. And in fact, sometimes we can see heat radiation being given out as light, and the brighter it is, the more heat radiation is being given out. Now, not only does the intensity of the peak increase, the wavelength of the peak decreases. So let's have a look at this example here. Okay, we've got a red star, which is quite cool, and we can see that the peak is about 700 nanometers, which is about the wavelength of red light. Okay, we've got a yellow star, which is slightly hotter. Now, not only is that yellow star brighter, but also its peak wavelength is slightly shorter. So it's now moving into the yellow colour range, because if we remember, blue is the shortest wavelength and red is the longest. Now, when we move into a blue star, this is a really hot star, and so our peak again has increased. Not only has it got higher, it has also moved to shorter wavelengths. So this has done two things. As our object gets hotter, the peak increases, as you might expect. But not only that, it goes to a shorter wavelength. Okay, so hot objects emit infrared radiation waves, but they don't just emit infrared radiation. They emit a range of wavelengths around infrared, so that's why they can emit visible light or even ultraviolet if they get hot enough. The amount and type emitted depends on its temperature. So the hotter the temperature, the shorter the wavelengths emitted. Okay, so what is ultrasound then? So ultrasound is sound or vibrations above human hearing, or above 20,000 hertz. That's the number you need to know. So how does ultrasound imaging work? Well, there is a partial reflection at each interface. So ultrasound is what they might use with unborn babies to look at them. There's a partial reflection at each interface. You shine this ultrasound in. I say shine, really send it in, transmit it in. At every boundary, for example, between skin and bone or between skin and fat, there'll be a little bit of reflection and some transmission. So some passes through, a little bit gets reflected back each time. The reflected pulse is detected and used to work out the time delay between layers. So if you've got multiple layers, each time the light goes in, there's a little bit of reflection, and the time delay from each reflection can help you to work out the distance between the layers. So here's an example of a picture you may see in the exam. So here is something being emitted onto the skin, an ultrasound pulse being emitted onto the skin. And this is the first partial reflection from the front of the bone. This is the second partial reflection from the back of the bone. These could be two tiny little partial reflections as it enters the bone marrow on the inside of the bone. And in the exam question, they'd be likely to tell you maybe what the speed is of ultrasound in that medium, in that flesh or bone, and the time delay of that as it passes through it, letting you work out the distance s between the layers, so you can work out how far away an object is, for example. Okay, so it gives you fuzzy images, but it is really safe. It's much safer than using X-rays. If you think about imaging fetuses, we don't want to expose those to cancer-causing radiation. So it's used for a few things. Used for destroying kidney stones. They'll shake the kidney stones to pieces, and it'll pass out of the small pieces will pass out in urine. Can be used for cleaning maybe antique watches, very delicate material, detecting flaws or cracks inside building materials. For example, steel girders used for skyscrapers. Got to make sure there's no faults in those before they're used. So visible light and colour. White light is made of three colours: red, blue and green. Now, why can we see colours? So if we paint a wall red, red paint absorbs all the colours except red when you shine white light at it. So it absorbs blue and green and will reflect the red. Now, green paint absorbs all the other colours except green, which it reflects. Blue paint does the same. It absorbs all the colours except blue, which it reflects. Now, worth remembering this then, that black paint absorbs all of the colours and it reflects none of them. So the reason why things look black is because there's no reflected light coming from it. And white paint will reflect all light, so it will reflect the red, blue and the green, absorbing none of it. Now, how do colour filters work then? So a colour filter, like sunglasses, coloured sunglasses, a red filter absorbs all the colours apart from red light. So a red filter will allow red to be transmitted through it, hence why we look through a red filter, everything looks red. Blue filter works in the same way, and the same with the green filter. So the colour of the filter is the light that is being transmitted through it. Now, if we were to shine a white light onto a blue dress, why does it look blue? A blue dress will absorb all wavelengths apart from blue. Now, if you then got a red filter, because red filters only let red light through, and we're looking at a blue dress, the blue dress would appear black. Okay, if we use a blue filter, the blue dress would appear blue, and if we use a green filter, the blue dress would appear black. Okay, electromagnetism. So this includes the motor effect, electric motors and loudspeakers, the generator effect, generators, microphones, and transformers. So to start off with the motor effect, we need to know a little bit of science about what happens when you put current through a wire. If you put current through a wire, you get a magnetic field around it. Now, if you coil this wire up while you're putting current through it, there is a magnetic field around it, like you can see here, but they kind of add up. They add up to make it even stronger. So you can have a strong magnetic field around an electromagnet, and these electromagnets are used for various things, using magnetic trains in Japan, or picking up iron, steel in scrapyards. Now you can see here you need to use the right hand grip rule to be able to work out the direction of the field lines around a wire, and it works the same on a solenoid, on an electromagnet. You've got your fingers curling around the outside here. Your thumb is going to tell you the direction of the field lines. Okay, and here you've got your fingers curling around the wire here. Your thumb shows you the direction of the current, or if you put your thumb in the direction of the current, your fingers show the direction of the field lines. Okay, so your field lines and your thumb being the current, field lines being your fingers here. And that's called the right hand grip rule. Okay, so how can we use this with the motor effect then? So this is the motor effect. The magnetic fields from a magnet and a current carrying wire, so that's the wire that we've got current going through, that will interact and they'll feel a force between them. Now the wires have to cut through the field lines. That means that the wire has to be at 90 degrees to the field lines. They can't be parallel to the field lines. So if we want to increase the strength of, if we want to increase the size of a force, we have to increase the current going through the wire or the strength of the magnet, because there's only two things involved here: a magnet and a current carrying wire. So we increase the current, increase the magnet, makes it stronger. To reverse the direction of the force, well, we have to flip the magnet round, reverse the north and south poles, or reverse the current as well. Now, if we have a picture here showing this example, we've got to work out which way the wire might move. So this is a horseshoe magnet showing us north and south, and we've got a wire here which tells us the plus and the minus. Now, current always goes plus to minus. Field lines go north to south. Okay, so if we want to find the direction of the force, we've got to use Fleming's left-hand rule, and I'm hoping everyone's going to have their left hand out now to have a go at this. So your thumb shows the direction of motion, okay, as in the way the wire is going to feel a force. Your first finger shows you the field lines. So your first finger, and all at 90 degrees to each other, your first finger is going to go north to south. So you've got to orientate your hand so that that finger is pointing north to south that way. Okay, now your second finger is going to be at 90 degrees to those other two, so they're forming like three-dimensional axes, if you like. The current there is at 90 degrees, and that's going to go from plus to minus, as it says there, so from plus to minus. So we follow this round, plus to minus, so your second finger has to be pointed in towards, out of the computer screen towards you. Okay, so you should be pointing at yourself with your middle finger. Your index finger should be going to the right of the screen, meaning your thumb should be pointing upwards. And that, quite rightly, like it says on the picture here, shows us the direction of the force there. Okay, so if we want to show which way a motor will spin, well, all we have to do is we've got to make sure that we're picking one side of the coil. Okay, because if we have a look at our same rules of applying the motor effect here, this side of the circuit is positive, this side is negative, so that means that this side is positive of the red line, the blue line there is negative. Our current is going to be going from plus to minus. It's going to be coming back on the other side. So we've got to just pick one side of the coil to work out whether it's going to be moving up or down. Okay, so let's pick the left-hand side of the coil then. So the left-hand side of the coil has got the current moving away from us. So our current is moving away. So your middle finger wants to be pointed into the screen. Now our field lines are going to be moving north to south. So your index finger wants to be pointing to the right. And there's just some builders drilling outside my room, so apologies if you can hear that. But your index finger, showing the field lines, wants to be going that way. Now that should mean that your hand is upside down and you've got your thumb pointing downwards. So we can see that this side of the wire is going to feel a downward force. Now just because we can, we're going to show off with the other side and just quickly double check that. So get rid of this here. Okay, so now we're going to pick the blue side of the wire. Blue side of the wire, we've got our second finger coming towards us, so you should have your middle finger, that's really, really helpful. You should have your middle finger pointing towards you, and you've got your field lines still going that way, and you should have, therefore, your thumb pointing upwards. So on the right-hand side, that's going to feel an upward force. The left-hand side is going to feel a downward force, meaning that your motor there is going to spin anti-clockwise. Okay, clockwise, the direction of a clock, anti-clockwise, the other way. Okay, let's have a quick look at see how how loudspeakers work. So this is a picture of a slice through a loudspeaker. Got a few features here I just want to talk about. We've got a permanent magnet, and this magnet is, if you were to look at it from above, it would look a bit like that. We've got a central spoke and then a raised area around the edge. Okay, but when you slice through it like so, you can see you've got a raised edge around the outside, which is your south poles, and in the middle you've got this north pole sticking out. Now wrapped around the north pole is a length of wire, and that length of wire, just like our electromagnets, is wrapped around there, and through the length of wire we've got an input voltage. So as you can see here, it's an alternating current which goes up and down, and an alternating voltage which goes backwards and forwards. Okay, attached to this coil in here, we've got a really thin paper cone, and that's why your speakers are very fragile. You don't want to be poking them because this paper cone is very lightweight and quite fragile. And of course the job of it is to produce sound. So sound will come out, electricity goes in. That's the job of a speaker. So let's have a quick look and see how it works then. So AC current will be sent to the coil, and this coil is attached to a paper cone. So AC current comes in. Now the coil is inside a strong magnetic field. We've got a permanent magnet in here. Now when the current is flowing, it generates a magnetic field around the coil. So we can imagine field lines maybe coming out of our our coil there. And those field lines are going to interact with the magnetic field lines from our magnet. So this interacts with the magnetic field lines from the magnet and generates a force. So when two magnets interact, they'll feel a force to each other, which moves the cone. Now as the current alternates back and forth, it moves the cone back and forth and creates areas of compression, probably these bits, and areas of refraction, maybe these bits, which are sound waves. So air particles being squished up and spread out. Now the frequency of the sound waves are the same as the frequency of the AC current. Okay, so generator effect then. Instead of using electricity to make kinetic energy, we can reverse this process and turn movement into electricity. So we will need a magnet and a coil of wire, but instead of putting electricity in to get movement, we're going to put movement in to get electricity. So the generator effect is the induction of a potential difference, voltage, across a conductor, and if it's in a complete circuit, it will turn into current, when the conductor experiences a changing magnetic field. So, in other words, you get a wire, you move a magnet around near it, because the magnetic fields are changing across that conductor, it's going to make it have a voltage in it. Okay, so how can we affect the size of the current being induced? Here's my ammeter reading to measure the size of the current. As I move that magnet in and out, and I have to keep moving it, as I keep moving it, it's going to generate current for me. Now, if I move the magnet faster, we get a bigger current. What affects the direction of the induced current? Well, the direction of the movement of the magnet. So if I push the magnet in, we're going to get current one way. As I pull the magnet out, we're going to get the current the other way. And if I was to switch the north and south poles round, we would find that would change the direction of the current. Now, when a current is induced in a conductor, the induced magnetic field opposes the original change. So what does that mean then? Well, when I push in a south pole into a coil of wire, moving this magnet into the coil of wire will create a current inside the coil of wire. That current inside the coil of wire creates a magnetic field around the coil of wire. So, but the direction of the magnetic field that I create will always be in the opposite direction to the one that I'm introducing. So as I pull a south pole into a coil of wire, it will create a south pole there to try and repel it. And as I'm pulling a south pole out of the coil, it's going to create a north pole to try and attract it. So they will create a pole that wants to oppose the original change. So if I'm pushing in a south, it's going to create a south to repel it. If I'm pulling out a south, it's going to create a north to try and attract it. Okay. So applications of the generator effect. So these generators that we can make then. So an alternator. An alternator is the standard generator that's used in power stations and wind turbines. So this is what will be attached to the blades of a wind turbine in one of those tall towers. It produces AC electricity. So as the coil is rotated by wind turbine or a steam turbine, it cuts through the magnetic field lines of the magnet, which will be moving north to south. And as one side of the coil moves upwards, as this one moves upwards, the current will flow. But as it spins, that same side moves down through the field lines, the current will flow in the opposite direction. So current will flow one way when it's moving up, and then when that same side comes back down the other side and is cutting through the field lines the other way, the current will swap direction. So this produces AC current that we should be able to see. That should look like so. Okay, and here we have our oscilloscope trace of the potential difference generated by an alternator. And of course, if it's connected in a closed loop in a circuit, that will also create current. So the dynamo then. The dynamo is used in batteryless bicycle lights and maybe wind-up torches as well, and it produces DC electricity. So this has got a split ring commutator, which is just a device used so that as the coil flips over, it doesn't let the current go back through the other way. So this has got a split ring commutator. The connection swaps every time, so it keeps the current flowing in the same direction each time. So it produces DC current. And when we see that, we would see a kind of like just the positive side of the alternating current. Now, when we take an average of that, when we take an average of all those dips, we would see a smooth line just going through the average there. So this is an oscilloscope trace of the potential difference generated by a dynamo. Okay, so how do microphones work then? So a microphone is basically a speaker in reverse. So if we have a quick look at this, we've got sound waves coming in. We've got peaks and troughs and compression and rarefaction. That will make a speaker cone move. That's attached to a coil of wire. That coil of wire is inside a magnet. So a thin cone moves backwards and forwards when waves hit it. The cone is connected to a coil of wire that's in the magnetic field. That coil of wire is going to move backwards and forwards. As the cone moves, so does the coil of wire. The moving coil cuts through the field lines of the magnet, of the magnetic field lines. This creates an alternating current in the coil with the same frequency as the sound wave. So this little coil of wire will bounce backwards and forwards because of the sound waves hitting it. And as that bounces backwards and forwards, it's going to cut through the field lines at that same frequency, generating a signal coming out, a little electrical signal coming out. Okay, and we've got transformers here. So transformers are used in the distributing electricity nationally, and it only includes, the national grid only includes this bit here, our step up and step down transformers and our transmission cables. And what do we need to know about these? Well, the transformer itself, what it'll have is it'll be made up of two halves. You'll have what we call a primary side and a secondary side. So if we look at a step down transformer that we've got here, inside this step down transformer, you'll have cables from the transmission lines there coming in on this side. So because it's a circuit, you've got the circuit coming in and coming out. And you can see lots of coils of wire on this side. On this side over here, you've got our secondary side, so that's going to be the one for the consumer. So off to our house. So again, we've got our completed circuit, so coming in and going out again, and you can see that there are fewer turns on the coil on this side. This is made of iron, this block here, but the iron does not conduct electricity. These little wires here will be wrapped in plastic, and there'll be no electricity conducted through the block. But what you can see instead is that there is a magnetic flux, as in a magnetic field, a changing magnetic field in there. So let's find out a little bit more about what we can work out here. Okay, well, if we know the number of turns on one side and we know the voltage that's being put in on that side, well, we can work out, if we know the number of turns on the other side, we can work out the voltage on the other side. So we can see that the ratio of the voltages and the rate is the same as the ratio of the number of turns. Okay, so if my voltage on this side is 200 volts, for example, and on this side it was 100 volts, well, it also makes sense that the number of turns have gone down by half as well. So if I had 50 turns on this side, I would only have 25 turns on this side. So the ratio of those two things, the ratio of the voltage to the number of turns, or the ratio, sorry, of the voltages to each other is the same as the ratio of the number of turns to each other. So 200 over 100 is the same as 50 over 25. Okay, so voltage in the secondary coil over voltage in the primary is the same as the number of turns. Okay, so just shortened into VS for secondary, VP for primary. Now we can also say that because these are really efficient, these transformers, they don't lose much energy, we can simplify an equation that says that the power in equals the power out for a transformer. And so we can do, this helps us because we might be wanting to calculate the current possibly coming out of a transformer. So because P equals I times V, we can simply swap in V and I for power. So Vp times Ip equals Vs times Is. Okay, looking at our transformer again now in a little bit more detail about why exactly does voltage get induced on this secondary side? How does that happen? Okay, so we get AC current goes into the primary coil. So we've got an alternating current coming in on our primary side. The primary coil produces a constantly changing magnetic field. So when my current is going one way, the magnetic field lines are, let's say, coming out this way. And then when I switch my current the other way round, so my current is now coming out at the top here, we're going to have these same field lines, but now they're going to be coming out at the bottom. And into the top. So by switching the electricity backwards and forwards, the magnetic field is changing backwards and forwards. So we've already heard some science then about what happens with changing magnetic fields. So the changing magnetic field is felt by the secondary coil. The changing magnetic field is kind of guided by the iron core, and it's felt by these wires here. These wires here are in that changing magnetic field. So this induces, this creates an alternating voltage in the secondary coil. This is called electromagnetic induction, and the secondary coil will experience the same frequency voltage as the AC current in the primary, as the primary voltage as well. So whatever voltage is in here, so whatever frequency, as in how many times per second it's flipping backwards and forwards, this one will flip backwards and forwards by the same number of times per second. Okay, on to our space topic, our last four areas to have a look at. So solar system, life cycle of stars, orbital motion of stars, and redshift, evidence for an expanding universe. So the solar system, within our solar system there's one star, the Sun, plus our 8 planets and a few dwarf planets that orbit around the Sun. Now natural satellites, they're the moons that orbit planets. They're also part of the solar system, and there's hundreds of moons in our solar system. Our solar system is a small part of the Milky Way galaxy, so around 100 billion 100 billion stars in our Milky Way galaxy. Now, the Sun was originally formed from a cloud of gas and dust called a planetary nebula, which was pulled together by gravitational attraction. And this leads us nicely onto our stellar evolution, so our life cycle of stars. Now you get three different types of stars, which have got three different types of endings. Light stars, which are up to about 8 times the mass of our Sun, medium stars, and massive stars. So let's have a look at what all stars start off as then. So the force of gravity will attract dust and gas in a vast region of space full of dust and gas. Eventually, as they start to fall down, the force of friction will warm them up, and they get so hot as they fall down that they will actually start doing nuclear fusion. And when they do nuclear fusion, they'll basically turn on as a light. Now, once they've lit up, once they're doing nuclear fusion, they'll be converting hydrogen into helium in nuclear fusion. They become what we call a main sequence star. So our star at the moment is a main sequence star. And every star that lives will go through this phase, even if it's just briefly. So we're going to start off with the sequence of lightest stars. So the lightest star, like our Sun, would go protostar, main sequence star. Now, as it starts to use up its fuel, and it runs out of fuel here, it's going to expand rapidly into a red giant. And once it's gone into a red giant, it's going to carry on burning the rest of its fuel above helium in the periodic table. And once it's used up all of its fuel, it's going to start to shrink back down again into a white dwarf. So the force of gravity would pull that back into a slightly smaller size. And as it keeps cooling down, it keeps on using the last of its fuel. Eventually, it's just going to fade away into what we call a black dwarf, where we can't see it anymore because it doesn't give out light. So that's the pathway of our lightest stars, like our star. Now we have other stars which are much more massive than ours. Now these ones, after being a main sequence star, after burning up most of their hydrogen into helium, the heavy mass stars would then form a red supergiant. So a giant again, but this time a supergiant because they're very special. And these ones, once they've used up the last of their fuel, they will collapse inwards really rapidly. They collapse inwards so rapidly that when they collapse, they explode outwards in one of the largest explosions in the universe called a supernova. So the explosion of a star or a dying star. Now during the supernova is where they will make elements which are heavier than iron in the periodic table. So all of our golds and uraniums and silvers, they'll all be made in a supernova explosion. Now, after the supernova explosion, and that's ejected lots of material into space, lots of those elements into space, what will be left behind is what we call a neutron star, which is made of neutrons and is very, very dense. Now, the most dense stars, the heaviest stars, about 10 times the mass of our Sun, well, they will actually go through the neutron star phase straight into a black hole. And a black hole is where mass itself has collapsed in on itself to have no size, and hence they can't be seen because they've got no size. But they're still incredibly heavy with a very strong gravitational force. Okay, so orbital motion. So orbital motion is the science of objects rotating around a fixed point. Now, velocity is a vector quantity, and so it includes both the magnitude of speed, like the size of the speed, and it also includes the direction as well. So when something is in circular motion, the velocity is constantly changing because the direction is changing. So even though the speed can be constant, the direction is changing, so we can say velocity is changing. Now, if velocity is changing, that's the same as saying something is accelerating. Its velocity is changing, so it's accelerating. So we've got an object here which is being pulled towards the centre. Let's say it's a concher on a string. The force will always be towards the centre of the circle. If you were to snip the rope at any one point, the object will carry on at a tangent to the circle there and will carry on going at 90 degrees to the direction of the force that was pulling it in. Now, the example of uniform circular motion or orbital motion that they use in the exam board is planets orbiting stars. So if a planet or a moon is in a stable orbit, stable meaning that the distance of the object from the planet is staying the same, if the speed changes, the orbit radius has to change too. So if you make the radius smaller, or you make it's the same as making the speed faster. So something will orbit a planet much faster at a smaller radius. The further away from the planet it is, the slower the speed it can have. And this is because the force of gravity is stronger near the object. So because the force is stronger, it'll make it rotate quicker. Okay, so redshift then, evidence for an expanding universe. So how do we know that the universe is expanding? Well, when we look up at distant galaxies in the sky, the light is more red than expected. The only way to explain this red light is because the galaxies are moving away from us. So the redshift effect is, the further away a galaxy is, the longer the wavelength of light we receive. The further away the galaxies, the faster they're moving and the bigger the observed increase in wavelength. This effect provides evidence that space itself, the universe, is expanding and supports the Big Bang theory that states that all matter started in one place. So let's have a look in a bit more detail then. So when an object moves away from you, if we've got a star here, a galaxy rather, which is moving to the right, if you've got someone watching it moving away, as in the galaxy is receding, then those light waves which are given out become stretched because the galaxy itself is moving. Now if for example you had a galaxy moving towards you, you would see that the light from that becomes squashed up because that object is moving towards you as it's giving out the waves. So the light waves will become squashed, we call that blue shift, and if the galaxy is moving away from you, the light waves become stretched, meaning redshift. So here's an example of the evidence that, a simplified version of the evidence that we use to prove that the universe is expanding. So if we've got a star which is at a fixed distance from us, we can see all the colours of the rainbow that come out of that star. And the star has what we call absorption lines on it. These are lines where those wavelengths, those particular frequencies of light are being absorbed by the elements in the star. So hydrogen, helium, any other elements in there. And they will absorb specific frequencies of light that comes out of the star. So these are called absorption lines. And those absorption lines are due to the elements in it. So we know what those elements are because we can recreate them on Earth. So if the star is at a fixed position, we get kind of a yellowy light coming out of it. Now, when we look at a object which is moving away from the Earth, and we have a look at those, the absorption lines are moved slightly to the red end, ever so slightly to the red end. So these are further away, and so this tells us that the object is moving away from us. Okay, and if we've got the galaxy is moving towards us, then we see that the star is blue shifted. Evidence for the expanding universe. How does this prove it? How do these absorption lines prove it? Well, light from distant galaxies is more red than expected. The light is shifted to the red end of the spectrum. Here's our colour spectrum. The light has been shifted over, these absorption lines have been shifted over to the redder end of the spectrum. The further the galaxy is away from us, the more redshifted it is. So those absorption lines are moved even further away. If we rewind the positions of all the galaxies in the universe that we can see, and we were to rewind them all, because we can see they're all accelerating away from us, if we were to just rewind all of that, we see that they start off in one place. Ladies and gentlemen, that covers all of the separate content for Physics Paper 2. Thank you very much for watching, and good luck.